A comet from interstellar space, 3I Atlas, does something we've never recorded before. It grows a tail that appears to be pointing toward the sun. And behind the scenes, global emergency protocols quietly kick in. This isn't sci-fi speculation, it's real. Captured in high resolution by the Gemini South Observatory in Chile and Teide in the Canary Islands, a narrow stream of material, dust or ionized gas, is visibly stretching in the wrong direction. Not away from the sun like every other comet we've ever studied, but toward it, directly into the heart of our star. Almost instantly, the object is flagged for reprioritization. JWST's internal anomaly detection system sends a directive to switch spectral focus. Hubble begins tracking it more aggressively. In a matter of hours, this icy visitor isn't just an interstellar curiosity anymore. It's marked as a high-interest non-local object, and that triggers protocols. We're talking internal responses at NASA. Observation drills begin within the European Space Agency's planetary defense network. Some sources say even deep space monitors typically used for space weather are quietly retasked. But here's the question no one can answer yet. And the one that matters most. Why would a comet's tail, a tail formed by solar radiation and plasma wind blasting material away from its surface, be pointing toward the sun? That's the mystery that set off this chain of events. Not because it posed a clear threat, but because, if confirmed, it would break a fundamental rule of cometary physics, a rule we've relied on to understand how these icy bodies behave near stars, near us, near Earth. And when something that's not supposed to happen suddenly does, that's when people start paying attention. The images weren't fuzzy. They weren't ambiguous, and they weren't a trick of the light. Both Gemini South and Teide Observatory locked their instruments on 3I Atlas as it closed in on its approach. What they captured wasn't just a comet behaving strangely. It was behaving impossibly. On the sunlit side of its nucleus, a tightly collimated plume was visibly blasting toward the sun. Not a broad fan of dust dragged by radiation, not a fading trail in the solar wind, but a direct forward-facing jet. The astronomy teams initially assumed an optical illusion. Maybe we were seeing the tail edge on, or maybe it was a brief moment of overexposure. But follow-up exposures confirmed it. The plume was real. It was active, and it was violating the known playbook of comet dynamics. This wasn't just a photographic curiosity. It was something that required explanation fast. On Earth, jets like this would come from high-pressure vents or controlled nozzles. In space, comets sometimes shoot out narrow geysers when a sunlit surface cracks and suddenly releases frozen gases. That's what some scientists proposed here. A sunward vent blasting heavier than usual material. But here's the problem. Those events are normally short-lived, faint, and often lost in the wider outgassing noise. This plume, it was stable. It lasted hours, maybe longer, and then came something else. A faint, almost ghost-like countertail still extended behind the comet, as expected. But now the question was no longer about what followed the comet. It was about what was leading it. Was this plume a jet of heavy dust? A column of high-energy ions, or something else entirely? Some interaction with solar magnetic fields we didn't fully understand. Because if this wasn't just a jet, if it really was a tail, an extended directional flow of ejected matter toward the sun, then every assumption we have about how comets behave under solar influence just took a hit. And more urgently, it raised another possibility. What if 3I Atlas wasn't reacting to the sun, but interacting with it? While visual data had everyone's attention, the chemical data quietly turned up the pressure. The James Webb Space Telescope turned its infrared spectrometer on 3I Atlas in early August, and the results came in just before the tail anomaly erupted. What it found wasn't just interesting, it was deeply unexpected. A staggering 8:1 ratio of carbon dioxide to water vapor. That's not normal. Not for solar system comets, not for the interstellar object Borisov. Even among the oldest, coldest Oort cloud bodies, CO2 rarely dominates like this. But 3I Atlas, it's not just CO2, it's borderline CO2 dominant. Some astronomers began whispering about its origin. Could it have formed in a carbon-rich stellar nursery where water was scarce? Could it be the frozen exhaust of some ancient planetary atmosphere, chemically stripped and deep frozen, drifting for billions of years before falling into our gravity well? Or more provocatively, could this unusual chemistry be related to the jet? CO2 behaves differently than water. When exposed to solar heating, it sublimates faster. It expands harder. And in a low-gravity object, that means stronger directional thrust, which leads to the obvious speculative leap. If the tail is driven by carbon dioxide and not water, are we looking at a fundamentally different kind of comet, or something engineered to behave that way? That CO2 ratio doesn't just challenge our models. It hints at chemistry we haven't seen since Borisov. And even that wasn't this extreme. If the sunward plume and the CO2 dominance weren't enough, the next discovery pushed things over the edge. Spectral data from the Keck Observatory in Hawaii and the Very Large Telescope in Chile revealed something that flat out shouldn't happen. Vaporized nickel, but no detectable iron. That's like finding smoke without fire. In every known comet, asteroid, or meteoritic fragment we've studied, nickel and iron show up as a pair. They form together in planetary cores. They're fused in high-temperature environments and vaporize under the same thermal conditions. Where there's nickel, there's always iron, until now. But in the coma of 3I Atlas, Keck's instruments saw clear signatures of atomic nickel and nothing from iron. Not a trace. Astronomers went back to check the instruments. They reprocessed the data. The results held. The working theory: nickel-carbonyl compounds, exotic molecular bonds between nickel and carbon monoxide, might be responsible. These are fragile, rare, and volatile even under lab conditions. They could exist in deep space comets that formed in ultra-cold environments where chemical evolution took a different path. But if they're here and breaking apart under solar heating, that means this comet is chemically distinct from anything we've catalogued. And here's where it gets uncomfortable. Some researchers noted that nickel-carbonyl compounds have industrial applications. They're used in metal purification. Some called that an irrelevant coincidence. Others not so sure, because if 3I Atlas contains materials rarely seen in nature, and they're being ejected in a directional jet, the speculation practically writes itself. Are we seeing the breakdown of something synthetic? At this stage, no one's making claims. But the absence of iron, the precision of the plume, and the weird chemical profile, it's not adding up. And behind the scenes, data requests from government observatories began ramping up. More than one telescope was asked to submit full bandwidth logs in real time, which raises the next question. What exactly were they hoping to catch? So let's take stock of where we are. We have a comet, if we can still even call it that, throwing a plume of matter directly toward the sun. We have carbon dioxide outgassing at levels 8 times higher than water, a signature unheard of in both local and known interstellar objects. And we've got nickel vapor in the spectrum, but no iron. That breaks one of the oldest compositional rules in solar system science. This object may not be threatening us, but it's not behaving like anything natural we've catalogued, and agencies are treating it like a high-priority enigma. Internally, things have shifted quietly but noticeably. The International Asteroid Warning Network began running real-time trajectory drills, using 3I Atlas as the simulated object. Officially, it's just standard practice, but it's rare to see drills triggered this far out for a known non-impacting body. Then there's the SphereX mission, originally tuned for sky-wide infrared mapping. A portion of its data bandwidth was redirected. The same goes for NASA's SWIFT telescope, which typically monitors gamma-ray bursts and ultraviolet emissions.